Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Mario Suedholt, so I'm an associate professor at École des Mines de Nantes, which is one of these strange engineering high schools from France. But okay, I'm working in a group which is a joint group with INRIA, which is the major research lab in France. And okay, so what will my talk be about? Okay, so first I will give a motivation. Motivation because, twofold motivation, because I'm not, okay, most of you will probably already have heard about AspectJ and aspects. And okay, I'm not really working with AspectJ. My concern is what can you do beyond AspectJ in a certain sense. So that's the first point, expressive aspects, where expressive means in a certain sense more expressive than what you can commonly do with AspectJ. And then, okay, the second part of the motivation about aspects for non-sequential systems, because yeah, the situation is quite paradoxical in the sense that non-sequential system, distributed systems should be probably the prime domain of application for aspects because they are large, there are cross-cutting concerns and so on, and they are relevant in practice, but there was relatively few work done on that. Almost all of the work on aspects currently is on sequential systems. Okay, and then I will present two different recent approaches we have developed in that domain. One is about aspects with explicit distribution, so that in the aspect language you have means to explicitly refer to some distributed application. And then a second one, which is an aspect systems for concurrent programming. Okay, let's start with the motivation and just give an introduction also to the terminology. Okay, so I won't talk much about AspectJ, but okay, let's use AspectJ just as an introduction also for the terminology. So in AspectJ, what you can do is you can define an aspect, and an aspect mainly consists of two parts. A point cut definition, which defines when during the base program execution you want the aspect to modify something, and then an advice declaration, which defines the modification you want to do at those points. Okay, you remarked perhaps that I talked about when in a base program execution. Okay, you have the static view of aspects, which is modify the program text, and you have a more dynamic view of aspects, which says, okay, you have a base program execution, and aspects modify this execution. Theoretically, both are equivalent. You can do everything which you can do statically during the execution. In practice, okay, one or the other can be simpler depending on your runtime system and so on. Okay, so in AspectJ, you can define these point cuts. You have certain primitive point cut constructors like execution, which means execution of a method. So when a method is executed, so after method dispatch, you want to do something. And this example stems from a simple example the AspectJ guys use, which is quite interesting, which is update signaling in some kind of figure editor. So you have a figure editor with a nice traditional OO hierarchy, with an abstract figure element at the basis, and then, okay, you have derived figure elements, and each of these figure elements can update a display. And the question then is, okay, here for this aspect is, when you do an update, you want to do it once at certain places. And okay, that's a problem which even with this very simple hierarchy is very, very difficult to do in object-oriented programming. Basically, you can't do that without re-architecturing the application. So introducing some kind of event-style architecture instead of this plain OO architecture. Okay, and second point, which is important here, I will come back to that later, is these different primitive point cut constructors you can use in AspectJ. Execution is just one. You have many of them, but almost all of them are atomic in the sense that each of those denotes one specific execution event or a set of execution events, but doesn't allow to express relationships between different execution events. Okay, I will come back to that. So when we have a look at the characteristics of AspectJ, or the main characteristics, let's say, so we have these point cuts which match execution events. As I said, these point cuts are mostly atomic, so they denote sets of individual execution events. The exception in AspectJ is the so-called C-flow constructor, which which allows to match, for instance, a call, depending if it is executed within the control flow of another call. So this constructor can be seen as relating different execution points. So you have the execution point where the originating call occurred, and then later on you say, okay, this is still in the control flow, so this is still a point of interest to me. So you see the C-flow constructor can be seen as relating all of the execution points within the control flow of a call. So this expresses explicitly a relationship between different points. Okay, I will come back to that, the importance of that later. So then you have the advice, and AspectJ advice is mainly full Java. And then you have several aspect specific. So for instance, you have this proceed instructions which allows you to explicitly call functionality of the base program within the advice. So not using proceed in an advice, in an around advice, means that you don't call the base program execution. So you can replace the base program execution. Okay, and then there are 2 or 3 other small things like advice execution and so on. Okay, then you have the aspects itself, and aspects basically are sets of point cuts and advice declarations. And then in aspects you can define aspect internal state, which you can use in your point cuts, in your manipulate, in your advice. This aspect internal state can be some kind of view of the base program state. But okay, in aspects, in AspectJ aspects, you can also explicitly, directly access state in the base program. Okay, so point cuts can be execution related. So all of those point cuts constructors we have seen until now were that kind. So the execution of a method, the call of a method, so before a method dispatch, the C-flow constructor. And okay, in AspectJ you also have static point cuts. So static point cuts means that they modify the static structure of the base program. Okay, so that's a property of AspectJ which is quite important to some uses of AspectJ. But okay, I won't talk about that anymore because it's not interesting to me. And okay, what's more interesting to us in this context is, what about aspect composition? Basically, when you have different aspects, the difficult thing is when these different aspects interact. So when one aspect has a consequence that another aspect will behave differently. And okay, there are different ways to define such interactions. And but the important thing is that once you have these interactions, obviously you have to do something about them. And basically you do that by composing aspects in some way or the other. And in AspectJ you have only very restricted means to do that, because basically all what you can do is in AspectJ is you can partially order aspects. So there is a specific keyword domination relationship with which you can say, okay, this aspect should be executed before another one, dominate another one. You see, from a fundamental point of view, from a theoretical point of view, okay, this defines just a partial order among aspects. But that's all what you can do. So one of the interests of my work, which we will see later, is that in many contexts you want to be able to more flexibly define aspect composition. Okay, we'll come back to that later. Okay, now before I really come to the work I'm personally interested in, let's have a general look at AOP. So AOP for and against. Okay, I'm doing research on it, so I'm certainly not part of the persons who say AOP has all the nice solutions for the big problems we want to solve. The current state, more or less, is that you have some solutions for some relatively simple problems, and then hope that perhaps you will get some solutions for the really interesting problems. Okay, but what's the case for AOP? There is nevertheless a very basic case for AOP, in my opinion, which is cross-cutting is a real problem. When you take the simplest application of AOP, which is do some logging somewhere, then logging typically, when you have a plain programming languages, you have to modify at plenty of places your programs in order to do the logging. And then, okay, you need some means to quantify. Now, obviously, you can have specific frameworks to support that. So in In Java, for instance, you have these log4Java. Okay, unfortunately, I'm not that firm with the .NET framework. I don't know what the equivalent in .NET is, but very probably you will also have one. But nevertheless, there always remains the most basic thing that you have to modify. Yeah, all of the calls, for instance, you are interested in when you are really interested in the call context, so that you can't do it just by modifying the definition of a method. And in this case, obviously, AOP is useful because you can just quantify over those and then describe how you want to modify that. Okay, but that's only the simplest problem. The other, in my opinion, quite compelling domain where aspects should be useful is that of component platforms. And in component platforms, you have, for instance, these problems of distribution replication in the context of transactions. And everybody knows that the current way to do it is quite messy. And AOP should, in principle, provide a solution to that problem. That's exactly what AOP is about. But okay, that's part of the problems where AOP currently doesn't really provide the solution everybody could easily use. But okay, I will come back to that. And okay, the second point in the case for AOP is that that these problems typically are not tractable by traditional programming means. So when I come back to this simple example I mentioned before, this display signaling, then okay, the fact is simply that when you do first the nice object-oriented modeling of these figures, and then you have this problem of adding the update of the display, you can't just do that within this hierarchy. You have to introduce some kind of event mechanism or whatever in order to do that relatively nicely. And okay, then when the first 2 points, or in the context of the first 2 points, what does it mean when you say, okay, AOP, that doesn't really interest me and I don't use it? Basically what this means is that you will do the corresponding programming tasks which are behind log things, initialize and control transactions and so on. You will do that manually in your programming system. So basically, all of the drawbacks which AOP currently certainly has, I will come back to that, then they won't disappear because you don't use AOP. It's just that you have the same drawbacks in a less explicit manner, so someone will check out the files, modify them at many of places. Okay, so what's the case against AOP? And the case against AOP currently is still quite compelling, unfortunately. Okay, so the main line of argumentation against AOP is that basically AOP currently to a large extent is, you can see it as some kind of low-level transformation system. So you can define aspects. Your aspects basically define transformations on your base program. And then the question is, okay, what happens when you go beyond logging, tracing, monitoring? So these very simple applications of AOP. And there simply, fact is that currently at least when you do that, you quite rapidly get into trouble because you don't know exactly what the semantics of your aspects is. So you will get program problems in the evolution of your programs also in the presence of aspects, simply because you will start with one aspect, you will other aspects, you don't know exactly how they interact. People will change the base program and the aspects. Aspects typically are quite fragile. So when you change the base program, very often the aspects don't work anymore. Okay, and related to that is simply the problem that, what's the semantics of aspects? How can you analyze properties or verify properties over aspects? And okay, fundamentally, the properties of aspects involve the base program, pointcuts advice, and the non-local state of aspects and base program, in AspectJ, for instance. And this obviously poses a problem in that if any part of this equation here changes, then you have problems in getting to what your aspect should be. But okay, one principal reason of this problem, and that will get me back to my work, is the reliance on this notion of atomic point cuts in AspectJ, so that you really refer to individual points in your execution, and that you don't have the possibility to single out, for instance, sequences of execution events during your execution, which are of interest to you and which have to be considered together in order to really well define the semantics, let's say, of what your aspect should do at that point. Okay, I will come back to that now. So one way to in a certain sense, to tackle these arguments which make up the case against aspects is to consider more expressive aspect languages. So the goal then being that you get to more robust AOP. So, and the main idea here is to be able to make explicit relationships between execution events on your point cut language. So essentially eliminate use of non-local state, where non-local state includes the base program state, but also the state in the aspect, because for advice and so on, that's also some kind of non-local state. And typically, you have two means to do that. One is consider richer point cut languages. So there have quite a number of approaches now. So there have been approaches of regular aspects. So in your point cuts, you can use some kind of regular definitions. There have been approaches which use temporal logic-based aspects, logic point cuts, or whatever. Quite a number of approaches. But okay, all of those obviously are in the domain of research currently. AspectJ and the typical instances like Spring AOP and so on, they don't support this currently. And then there is a second means to attack this problem or make relationships more explicit, which is use at least domain-specific sub-languages in your point cut language, in your advice language, in order to express aspects. So in AspectJ, for instance, when you apply them to these component platforms like Spring AOP, then you don't have the possibility to directly express something about your distributed applications. What you do is you will use the abstractions which are provided by the framework, and then use those method calls finally in your AspectJ-like aspects. Which means, for instance, in this context of component frameworks, that you can't express easily relationships which directly involve clients and servers, which are very important. You always have to do that separately for each interface. So in your aspects, you will modify one part of the client interface, another part of the client interface, and also then you have to write a different aspects because it has to be applied on a different machine in order to define the corresponding changes which are necessary to the server. Okay, that allows me to introduce the second motivation of my work, which is, okay, let's have a look at non-sequential systems and aspects for non-sequential systems. And okay, basically, non-sequential systems typically are very large applications, and there are a large number of different concerns. So depending on how you implement them, distribution, persistence, transactions can all be concerns in the sense that they are scattered over your application code and that they are tangled with one another. So that they are cross-cutting concerns in the AOP sense. And so cross-cutting should be at least equally of equal importance than in sequential applications, and AOP therefore should be useful for those applications. When we have a look at the state of the art, however, we see that there is surprisingly few work in these domains, so on distributed and concurrent applications, AOP for distributed and concurrent applications. So the predominant approach, as I already said, is that you use a sequential AOP system with an existing infrastructure. So when you have a closer look at Spring AOP, JBoss AOP, it's almost exactly the AspectJ model. Okay, within this framework. So there is no, or at least few support really on the language level. It's just a framework, but basically the abstractions they provide are exactly the abstractions of AspectJ. So you have CFlow, you have executions, you can refer to calls, things like that. But, which means that you have these atomic point cuts once again, and you have no distribution-centric abstractions. So in these aspect languages, Spring AOP, JBoss AOP, there are no specific distribution abstractions for distribution. And this means that finally you will get very similar expression and correctness problems than for sequential AOP programs in that setting. Okay, now let's come to my second part, which is one specific approach, aspects with explicit distribution. Okay, ORD is the acronym we use for that. And in order to introduce that, let's have a closer look at one specific problem, which is transactional replicated caches. Okay, transactional replicated caches simply are caches where, okay, on each node in such a cache, you have a certain data structure, which is replicated in some sense to all of those nodes in one cache structure. And then, okay, you do the data replication under the control of transactions. So when you, for instance, abort a transaction, then you have to invalidate the replication actions you have eventually done over course of this transaction. Okay, there are very many different schemes, so I won't go into details of many different algorithms to do this replication or whatever. What I will do is, however, let's have a look at one specific implementation. So in the JBoss system, there is a specific subsystem for these transactional replicated caches, which is called JBoss cache. And we have done an evaluation of the distribution and transaction part in JBoss cache version 1.2. Okay, I insist on 1.2 because, okay, in the new version, it's a little bit different. I will come back to that later on. And, okay, so what we did is having a look whether replication and transactions in particular, okay, forget about the third one perhaps, whether this is a cross-cutting concerns in that implementation of JBoss cache. And okay, here in these diagrams, okay, I don't know whether you know these diagrams. These are diagrams constructed using the graphical user interface of AspectJ, the Eclipse plugin of AspectJ, which allows you to analyze code and graphically visualize where certain instructions belonging to those concerns are used. So basically each column here corresponds to a file. And okay, here the different colors indicate that certain instructions which belong to these different concerns are used in those files. Okay, now, okay, in our study there were 3 of them, but the 2 which are interesting for us are the black and the gray one. So if I remember right, black is transactions and gray is replication. And you see, this is distributed a little bit all over these. Okay, this is one class, and this is all of a module. And okay, this class, tree cache in version 1.2, it had one class, 3,000 lines. And okay, in version 1.4, it has 6,000 lines. Okay, many of that are comments, so it's not all of it code, but it's quite a huge class, and all of those together is also that's a module of I think 20,000 lines of code or something like that. So. So you see this cross-cutting of these 2 concerns, replication and transactions by itself, is quite evident here. The scattering, at least, is quite evident. Now, obviously, this kind of diagram doesn't say anything about the relationship between the transaction code and the replication code. But okay, we did some evaluation, and in many cases, this is quite coupled. So you have many methods in the classes, also small methods in the classes, where you have to do something about replication and transactions, okay?
You do this categorization manually? Travis, how did you identify?
Yeah. Basically what we did for that is that we defined, what you have to do generally is you define a point cut, which defines what are the methods you are interested in.
Oh, so this is already aspect defined?
No. That is plain OO.
Right. So how do you identify what line corresponds?
Yeah, okay. That's what you do. What you do is you define an aspect. You only define the aspect in order to identify the places. It's not in order to restructure or whatever. So you define a point cut which says those and those method calls are relevant for replication, and those are relevant for transactions. And then the system just gives you such a visualization. You see, it doesn't. These aspect definitions were just, we made them just for the visualization.
Is that common?
Yeah, very, very common. Basically, okay, you see, the scattering is really obvious from that. So that's, in that sense, that's proof for scattering. Now, scattering alone doesn't say much. You see, when you do logging, everything is scattered also, but that's not very difficult. You see, when you have a specialized framework to quantify, okay, you can do that easily. So that's the second part. Then is are there important relationships between the transaction code and the replication code which you have to obey? And in fact, that's what I was coming to. When you analyze then more in detail what this here means, the different colored parts in the files. You see that in many places you have classes where there is transaction code and replication code together. So, which at least means that you have to call the transaction code in the right place, that you can, for instance, interchange the two and so on. So you see you have relationships which you have to obey between the two. So, and this means that the code is also quite tangled. And this means obviously that you have problems when you refactor when you want to refactor the replication of transactions, or when you, for instance, extend the replication policy. Okay, and that's the example I will use in the following. In JBoss Cache version 1.2, there was only this very simple caching strategy. So you could define one cache, and then every data which changed at one node in the cache would be replicated to all of the others. So you couldn't even define partial interest, let's say, to one data element. So you couldn't divide your cache in some subparts where you said, okay, this piece of data should be only replicated in that subpart and not all of the cache. And when you wanted to do such an extension of the replication policy, that was quite difficult. So the idea of our study was to provide means to facilitate that. Okay, I will come back to that. Okay, so that's this example. Don't replicate unnecessarily, and don't replicate huge objects if you don't have to. And okay, now the question is, when you want to do that in a direct fashion, so that's a distributed application basically, what do you have to do? Yeah, basically, or what should certainly be useful are distribution-specific aspect abstractions. So you should be able to detect remote events. You should, or it could be useful to remotely execute some code. You should be able to support distributed state. Okay, a cache by itself is some kind of distributed state. But okay, here we talk about some auxiliary aspect which allows you to implement that. And then, okay, you must also be able to distribute, to deploy distributed code, things like that. And okay, our approach then was an aspect language ORD which provides specific, explicit means to do that. So in that language you have remote point cuts. You can reference to remote hosts. So you can say with this host constructor you can really name concrete hosts. With this on constructor you can say, okay, a host where the advice should not run on. So this is because you can also talk about where advice should be executed. And then in that aspect language you can use sequence point cuts over such remote execution events. So you can say, I want to do something provided that on that node a certain data had been put in the cache, and that at another time on a second host some interest to that kind of data had been registered. And then I want to replicate only between the two nodes, for instance, and not all of the nodes. Okay, and then there is a second abstraction, which is remote advice. So in that language you can say, execute advice remotely, and you can choose between asynchronous and synchronous execution of advice with respect to the firing aspect. And okay, when you have different aspects, that makes me come back to this composition issue. When you have different aspects in which apply at the same execution event, then in that language you can explicitly say that composition should take place, and futures are used in order to manage the synchronization between these different executing advice. Because when you have different advice which apply, obviously it can be, or very often they are executed in a certain order, and one aspect will refer, for instance, to the result of the second aspect, things like that. Okay, and finally you have a notion of distributed aspects in that language. So you have you have explicit means for the deployment of code, for instantiation of aspects, and for sharing of state. So typically, by default, state of such aspects is not shared, but you can say share that globally. Okay, that will be probably quite inefficient in most uses, but you can also say share that among a group of nodes. Okay, so all of this language, the results have been published at AUSD and DOA. DOA is today. Yeah.
Maybe you come later to that, but so can you quantify over boosts, for example, and over certain properties of those hosts, like services they are running, or in which way?
Yeah, okay. In that language, you can just quantify in the sense that you can define sets of hosts in this host identifier. So it wouldn't be very difficult to integrate a small language to say, okay, for instance, another way to quantify, it's indicated implicitly here, we have a notion of group. So you can say, you can add dynamically hosts to groups, and then you can say, okay, that point cut should be evaluated only on that group of hosts.
It seems to be quite unlikely that in a real application I can name exactly the host in advance on which I want to do something.
Yeah, okay. So what you... Basically, okay, there are no other means currently in the language to refer to properties of hosts, let's say. But what you can do is, you can use some kind of wildcard, which refers then to all hosts, or all hosts in a group. And then you define, the intention is that you define the properties you are referring to by the other means for remote point cuts. That you say, okay, when the service corresponds to a certain method call, then you will use a sequence which ends with that method call.
I'm sorry, I understood you said that you could refer to all hosts where some event had happened. Do you have that quantification possibility? Or?
Yeah, as I said, the only you can add hosts to groups and then use that group as some kind of set of hosts in that host specifier, and then you have a general wildcard which is just all of the hosts. And then, okay, what you write, let's perhaps have a look here. Yeah. So basically, what you do is typically in that language, what you do is, yeah, okay, I'm interested in all calls to this put operation in the cache on all hosts which are not the local hosts. You see, that are all other hosts. And then you can use, okay, it's called on point cut, but what it basically defines is where the advice should be executed relative to where this event is matched. So basically, what you can do in this language is you can define sequences which match different events in order. Okay, in order with respect to the sequence. Obviously, that doesn't mean in order with respect to some kind of global clock. We don't have a global clock here. So a sequence of events, and then when your point cut matches some event somewhere, you can say, yeah, with respect to that node or with respect to this originating node, that you want to execute something else or on the local host or on a specific host. Things like that. You see, by the fact that you can identify the events you are interested in, and then relatively define where you want to execute the advice. In my opinion, most cases of what you want should be expressible. But okay, I'm not saying that this language is complete for all uses in all settings for distributed systems.
And sorry, why is the on primitive part of the point cut and not on the advice level? Because it's not a property of the joint points you're detecting. It's like the after or before. Yeah,
okay. One possibility would have been to put it in the advice specification. But okay, in the very beginning, you can see this on specifier also of defining. It doesn't put a restriction on where you match an execution event, but nevertheless it expresses a relationship between the advice and the execution event. So I'm right, it would have perhaps been better to put it on the advice level, but also for a historical reason. The student who first came up with that put it there, and it seemed a good idea in our first uses of it, and okay, then changed a little bit. Okay, so what you then, just an example for sequences. So basically what you can define in this language is some kind of finite state automata. You see here, you can just write, okay, we use the sequence keyword, but you see from a state you can go to several states and so on. So it's rather finite automata, finite state automata. But okay, in practice, very often just sequences are used, or very simple automata. So sequence seems still a good idea, just to use the sequence keyword. Okay, and then so what you can do is saying things like, okay, there is one point cut, or okay, you see this should be a point cut. Huh? It's not only a method call. You have one point cut which defines what a start cache event is, what a put event is, what a stop event is, and then you can go to somewhere there, and then you can refer to these states, to these steps here, in order to define really when an advice should be applied. So you see this point cut would say, okay, in this sequence, I'm interested in the second step, and then, okay, you can bind some parameters from there, and then link that to advice. Okay, here you don't have an advice definition, but.
So how should I understand the step condition there? Is it?
No, it's just a problem. So this is the sequence, but how do you simply refer now to a certain step in a sequence? Yeah, in order to define, okay, at that step, an advice should be executed.
Well, these S1, S2 are really states, right? They're not actions. They're states, right? So how should I think of step REPL S2? Does it say if you're in state S2, then this is true?
Yes.
Is that what it means?
Exactly. Okay. So next. Okay. So you have this possibility to execute advice remotely. So I already said you can do it asynchronous, synchronously. Communication between them is managed using future. And okay, these groups, I already mentioned that. Okay. So basically, advice then is similar to what you do in AspectJ also. The concrete advice you write. So you define just whether it should occur before or after, or instead of the execution event you have matched. And then, okay, here this is a point cut definition. In this case, a local put, and then okay, you write some instructions of what the advice should be.
Sorry, you have a proceed there in a before advice. Is that?
Yeah. Okay. Yeah. Okay. The example is unfortunate. In the language, yes, you can do that because every advice is modeled as a round advice. So before. Basically, you have a restriction that proceed should occur at the end.
I just wanted to know if you have.
No. There's nothing, no change in that.
Right.
In that respect. Okay, so to have a look, do we have a look? Okay. In order to have a look at the concrete aspect, so you see some kind of lazy replication. You would just do it by defining specific events you are interested in, and then doing the replication only for those events, and not for all events. And the runtime system, how it works, is that such an aspect will be deployed depending on the deployment specification, which is here all. You see the first all, so it would be deployed on all hosts. And then, okay, depending on these on specifiers, the advice would be executed on certain nodes or not. And okay, here do we use a group? Okay, I don't. Yeah, okay, there is some group here which is used, but we don't need to talk about that. Okay, so that's the language. Okay, I didn't give the syntax or whatever. Those you can look those up in the paper. Then, as an implementation basis, okay, we use the system which has been developed at Freie Universität of Brussels, VUB, which is the JAsCo system, which is a dynamic aspect weaver for Java. So that was initially a sequential system. So it just had some notion of connector registry in order to manage compositions of aspects. And you see, you could compose different aspects using such connectors, and then the runtime system would basically propagate representations of execution events to these different aspects depending on the connector definitions, which would then decide whether that execution event is relevant to them. You see, and then fire up advice if necessary. And okay, so what was interesting for us, or why we based the implementation for our language on that system, simply is first, It's a dynamic aspect weaver for Java, and we also had in mind that this distributed version should allow dynamic application for an aspect of aspects in distributed applications. It already supported this kind of finite state-based sequence point cuts. And okay, this notion of connectors which allows to explicitly model composition of aspects. So basically these were exactly the three properties we also wanted for our distributed systems. And you see, none of these three is shared by AspectJ. So now, okay, I will come back to that later. So what we simply did was basically we implemented a distributed version of it where this infrastructure can be deployed on any host. And then, okay, there is an extension. The connector registry has been extended in order to be able to propagate execution events among different hosts. Okay, so let's have a look.
So in general, I could imagine that this distribution of the events is the biggest problem in the implementation. So you want to keep the network traffic as small as possible. So do you have some techniques?
We can perhaps wait just for the next slide, because it gives a little bit more details about how the implementation has concretely been done. So what we did, okay, in order to do this propagation of representations of join points, we use JGroups, which is an existing framework to do some kind of multicast broadcast communication within networks. We use some kind of customized sockets in order to transfer information for C-flow point cuts or sequence point cuts. Remote sequences has been simply done then by an extension of the existing JAsCo sequences. Advice is simply activation of deployed aspects. As I said, depending on the deployment specifications, aspects are already deployed. And then when there is a non-specifier, okay, you don't have to move the code. It's already there. Whether that's the most efficient way to do or not, okay. We'll discuss that later. Aspect distribution, as I said, is done by connector distribution, also using JGroups. And then these specific features like state sharing, perimeter passing by value or by reference, and so on, can be implemented by all aspects themselves. Now, okay, to your question, we didn't really evaluate the efficiency of this implementation, and it's certainly not the most efficient implementation you can get. So that's completely open point, I would say, currently. So we did just one implementation, and okay, then we did some evaluations. Very often, nevertheless, when you use aspects in such a setting, the aspects are fired relatively infrequently. So as long as you are certain that the number of let's say the number of hosts involved in broadcast is not significantly higher than what you would do manually, that an individual call, remote call, is acceptably fast compared to an optimal manual implementation. There is some hope that should be reasonable, but we didn't do more than that. The problem. So what we did is, in for aspect infrastructures, there are certain well-known problems, efficiency problems. And for instance, in JAsCo, you have two quite elaborate mechanisms for optimizing the execution of aspects. So basically, what we did is then ensuring that these mechanisms can still be used even in this distributed system, and then that individual calls, remote calls, basically they are the factor of 1.5 compared to standard RMI calls, for instance, let's say. Okay, but there is certainly much work to do on that. Okay, so to finish this part, currently we have two ongoing applications with this system. So one is using that for web services, so distributed web service composition. Okay, web services are obviously part of distributed systems, but the composition of web services very often is done in a centralized version. So all of these most of these BPL approaches, very often they just do that on one centralized node. And here the idea was to do that in a distributed fashion. There are fewer approaches, so there are some papers by groups from IBM who are working on that in particular. So the idea was to use this language I just talked about for client-side concern integration. Client-side concern integration doesn't mean that you only have to do something on one node, but basically that you use the aspects in order to manage the communication necessary on the client side for these concerns. Okay, that's also a cooperation with a group from VUB, and I have currently a second project which is really an application of the language for the restructuring of a toll system application. So that's with cooperation by Siemens AG, and so I don't know whether you know, but in Germany they just installed quite sophisticated system for tolls. So you have automatic machinery on all highways, which just reads when trucks are just passing under, and then it's sent up via satellite to a centralized server and so on. And the idea there is Siemens, they are interested in being able to dynamically adapt the code in the sense that functionality could, for instance, be shifted partially from the server to the onboard units, things like that. And okay, so the idea is to use this aspect system in order to enable such an evolution. Okay, I now come to the last part of my talk. How much time do I have? Okay, so this is a little bit shorter. Okay, so the last part is about a new approach to aspects for concurrency. And okay, when we have a look at the state of the art there, it's very similar to distributed aspects. It's even worse. So there is almost nothing specifically for aspects for concurrency. So one of the very first aspect languages which has been proposed was on concurrency. So this was by Krista Videira Lopez, who was in the initial group by Gregor Quixales in Xerox PARC. And she defined, that was really one of the first language whichever was defined, COOL, which allowed to define mutual exclusion constraints. So in your aspect you can say that method should be executed in a mutual exclusive way with another method. So not much more. So you could just define this mutual exclusion relationships on base methods. Then there were some other more theoretical approaches, in particular the James Andrew in 2001, who defined aspects as concurrent processes. But it was a very specific approach, not general synchronization of aspects or aspects with base programs, but instead he was interested. He defined one specific weaver and then tried to define properties over that weaver. So it was a very specific approach. And there is not really much more. What people have been done is, once again, using sequential AO system with some kind of concurrency library. So for instance, there have been recent papers taking the new concurrency library of Java 5 and seeing whether using AspectJ you can improve on that implementation or better use them, things like that. But okay, once again you have a similar problems than before. So typically you don't consider several aspects in such a framework, which obviously isn't really realistic for real world applications. And once again, this means that you should have more better means to manage aspect composition. Okay, and that's basically the goal of this approach I talk now about, which is concurrent event-based AOP. And okay, that's more currently theoretical approach. So the first idea was simply, what can we do provided that we want to define the base program and aspects as finite state processes. The problem is, processes, process calculi, there are obviously many, and that idea just to define that is very straightforward. The problem then is that when you really want just parallel composition as your composition operator on such aspects and the base program, then this only works obviously if you have already defined the aspects in such a way that basically you have to make the weaving explicit then. Because parallel composition of aspects would only work if the aspects would already specify in some way how it would be woven through the base program. And that's obviously not what you want. What you want is that you have relatively natural expressions of your base program and of your aspects, and then that you can say, now those should go together. But when you do that, okay, we'll see an instance of that in a minute, then you can just use simple parallel composition. Okay, so the idea of this work was to go that way, to have simple definitions of aspects in the base and then see how we can still, in particular, compose them in a relatively straightforward way. And when you talk about aspect composition, then when you follow this typical AspectJ model for advice, that you say typically you have a round advice, you have some before part, you have this proceed, where you can call base functionality, you have some after part, then what you want to do in a concurrent setting is to be able to synchronize aspects with respect to these parts. When you have different aspects which apply at a point, you would be able to say the before parts should execute sequentially, but the after parts can execute concurrently in order to get maximum concurrency, you see. When you do that with traditional systems, AspectJ, sequential systems, and concurrency library, you can do that, but you would almost never get it right because it's much too implicit then. Okay, so we want to have composition operators for flexible synchronization. We want then to have a formal Weaver definition in order to do property verification. Okay, in particular, since we use FSP processes, we can then use a label transition system analyzer, which is some kind, it's a relatively simple model checker, let's say, for such systems. And okay, we also did a prototype implementation in Java. And okay, this work has just presented at Gypsy last week in Portland. Okay, so just to discuss a simple example, okay, let's take this simple e-commerce abstraction, let's say. So you see users can log in, they can check out, then they can browse some catalog. And then, okay, you have these update operations, and update operations are updates by the shop owner who changes his database so that the price changes. Okay, so let's have a look. So this is how aspects look, and basically this is some kind of other FSP expression or finite state expression if you want to, because you see this consistency aspect simply says once you have done a login, I consider the update. So I only consider updates within sessions. So when I do a checkout, this is an OR, when I do a checkout, I go back here. And okay, when I'm within a session, then I look for update events. And okay, when there are update events, what do I want to do? I want to skip that update and just log that the update should happen for later use, for instance. Basically, okay, this can be seen as some kind of simple consistency aspect because it suppresses updates when a user is logged so that the user doesn't see the changing price. So it doesn't in practice, it wouldn't obviously suppress the change in the underlying database, but it would suppress the change in the view the user has on that database. Okay, and another aspect could be a safety aspect, which whenever there is an update would rehash the views, for instance, and then would back up, for instance, the current state of the user once the database had been updated. And you see this is done independently whether a user is logged or not. Okay, so these are very similar to FSP expressions, but it's not the same. You see, basically, this is not a valid FSP expression in the sense that it wouldn't allow that in your base program, for instance, when in your base program you would have a browse operation, then obviously this browse operation in that case here could be interleaved, which is perhaps what you want, but not in all cases. And when in your aspect you would do something on browse or update in this case, when you have an update at another position, then just when you express that as an FSP expression and put that in parallel with your base program, you would get deadlocks, simply because the update is allowed here but not outside of sessions. So you see, in order to be able to use composition as the simple composition operator, you have to prepare the aspect, basically instrument the aspects and instrument the base program. Basically, that's the core of the approach, being able to easily define the aspects and then having a formally defined instrumentation scheme, which then allows you just to use parallel composition as your composition operator. And then, since you do that using LTSA for analysis over such system.
You quantified variable A stands for some remain less behavior or something like this. So in your examples, you always use it in tail position.
Yeah, okay. It's always in tail position, so that it's equivalent to FSP expressions, basically.
But you can also use it in the middle, basically.
Yeah, okay, but then you couldn't transform it. It wouldn't be equivalent anymore to an FSP expression.
Sure.
Yeah.
Okay.
So here it explicitly, so the language which is behind syntactically restricts it to tail recursive occurrences. Okay, so when you have interactions on common execution events, or interactions in this framework are on common execution events. So here, for instance, on update within sessions. This would always do something on updates, but this only within sessions. So here you have an interaction. It's a simple example where you have an interaction within sessions, and there is no interaction outside of sessions. And then, okay, you want to compose those, and when you compose, you want to be able to define, how to synchronize parts of advice. So you see here the skip basically references the point where the base execution or another aspect would be called, and the log would be something afterwards. And obviously, logging probably you can do it in parallel with the other things. There's no problem in doing that. So in that case here, you would be interested in being able to say that should be executed in parallel with something else. And now you see this instrumentation I talked about. There is not really a problem in coming up with an instrumentation. But the problem is then, can you have composition operators which are general, so that you can define them once and for all, and don't have to define composition operators for each specific aspect and each specific application of an aspect to a base program. So that's perhaps the main interest of the approach. So with the specific instrumentation we give, it works with flexible operations. Okay, the idea of the instrumentation simply is that you introduce specific synchronization events, which allow you to say, okay, here the before part starts, so I can do that. I have to synchronize there or not. Then you have the after part, and we have to synchronize or not. Okay, I won't perhaps go into the details here. Perhaps just coming to the most interesting case. So then you see you can define these composition operators in a general way. So you see this is the essence of composition operators, which we have called par end, so which is some kind of parallel. And okay, end, we will see why afterwards. And basically the intention of this par end is that you execute concurrently before the before part of multiple advice, that you execute concurrently the after part, and that you proceed with the base functionality only if both aspects proceed. So you see, obviously, when you have different aspects which may proceed or skip, then you have the choice. When should the base functionality be executed or not? So there are also parallel operators which proceed when there's only one of those.
So I don't understand how before and after factors into this, because I mean, if I have an after advice, it already assumes that you're proceeding before, right? So I mean, you can't even run the advice.
Yeah, okay. The additional point which is missing here simply is the point proceed and skip always serves as a synchronization point.
Okay,
so there's always synchronization on that point.
So you're saying that I no longer have really before and after, I only have around advice.
Yeah, okay. We only consider here around advice in that formula. But okay, before and after simply is just around advice where you don't have after or before.
Right, where we certainly always proceed, right?
Yes.
But
yeah, okay. What's different with
my question, right?
Yeah.
If proceed is your synchronization point, which makes sense, then if I have before advice, let's say, does that will always run basically, right? Before I continue to
before will always run, yes.
Okay.
So the question here is, when you have different aspects which apply at the same point, will the before advices be synchronized or will they run concurrently? So, and that's what the operator allowed to express here. depending on which operator you use, but before advice will be executed synchronously or not, and same for after advice.
So the question I had is, say you said that some aspects might skip the proceed and not actually do the proceed, right? What if you have such an aspect and you have some before advice? Does the before advice actually run?
Yeah, okay, so in our aspects, you always have to say skip or proceed. So in all aspects, you have that synchronization point, and before advice is always run. So skip.
Even if there's not actually going to be a proceed.
Ah, you mean before advice of the called, Yeah, that's depend.
It's kind of a funny case, right? I suppose you have two aspects. One is just a normal before, which always proceeds. Another one which sometimes does a skip. It doesn't always proceed, right? So now you're saying the synchronization is the proceed case, right? Well, in this case, there's not going to be a proceed. Well, if there's no the proceed, does it make sense to run the before advice?
Yeah, okay, I see what you mean. In principle, you could define different operators, which would say to you, skip it completely, skip it. Yes, currently the semantics is that the before advices will be executed in any case. And then
after advice, not necessarily.
Yeah, after advice and the corresponding base functionality, not.
So after advice only executes if the proceed actually happens in all aspects.
Yeah. So
that's not uniform, right?
Yeah. Okay. What you can do is that's the case with this parallel, but you have other operators. So sequential, for instance, which sequentializes, and then the skip of the first. You would encounter the skip of the first advice early enough so that you can cancel the second. So you see, it depends on the operators which you have. Okay, so I won't go into the details, but the point then is that you can define these operators once and for all with the instrumentation scheme we have devised. So you take this definition and you can use it with any aspect. You don't have to redefine it, any aspect and base combination. Okay, and in our example, then you would get something like, you see, since this is parallel and proceed everywhere, you would get basically all of the interleavings between the before parts and the after parts. Okay, and then you can use these model checking techniques to determine to verify automatically some safety properties, absence of deadlock, some liveness properties. And you can also, either with the tools or manually, prove general properties of operators, such as associativity of certain operators, things like that. Okay, so that allows me to conclude my talk. So, the first major point of my work, basically all of my work, is that expressive aspects could be a mean to tackle these drawbacks of AOP. So that AOP is too low level, that you don't have guarantees over aspects and so on. Then distributed and concurrent applications are subject to many cross-cutting concerns, and AOP should be useful for their modularizations. There are a few approaches, and these approaches I presented basically are the first which do something non-trivial with domain-specific abstractions, let's say, for distribution and for concurrency. So, and what we are currently working on mainly is composition operators for distributed applications, formal semantics and property support, at least for a subpart of that distributed language. And then also, introduce causality guarantees for distributed aspects. So perhaps using these well-known algorithms in distributed systems, which allow you to have at least for some subpart of your network some clock which you can reasonably use. And for this concurrent part, we are working on an extended set of composition operators and then on an efficient implementation in mainstream languages. Currently, we have a prototype implementation in Java, but it's really just prototype. It's just you have synchronization points everywhere, and then there is some kind of global monitor which lets all of the different parts proceed or not, depending on what current composition you are considering. that was my talk. When you want further information, have a look there. And thanks for your attention.